Born-Haber cycle. Now, for any ionic solid, it is always very difficult to know its lattice enthalpy values. These values cannot be calculated experimentally, and they have to be calculated by some indirect method. Born and Haber, they devised a method by which this lattice enthalpy values could be calculated indirectly. For this, they used thermodynamics, and based on Hess law, these values were calculated by them. They gave a method, right, which was based on Hess law, and this law says that for any process, the total heat change which occurs is always equal to the sum of the energy changes which occur during the intermediate steps, all the intermediate steps of that process. And therefore, let us take up this example of formation of NaCl and let us understand how this can be done. Now, you know that NaCl is an ionic solid, so we will make a list of all the intermediate steps which occur during the formation of NaCl and would try and understand how the value of energy can be calculated. Right? We begin with the first step. The overall reaction of NaCl formation is solid Na plus half Cl2 gas gives NaCl. Now, the first step here is Na solid undergoing sublimation. Now, this Na solid which undergoes sublimation, it gets converted into sodium gas. Now, the energy change which occurs during this process is about 108 kilojoules per mole, right? And it is 108 kilojoules per mole. Step number 2 then would be the ionization of sodium gas. This sodium in gaseous form would undergo ionization, and the energy involved here will be called ionization enthalpy, and this value is about for sodium gas is about 496 kilojoules per mole. You can see that these values, they come out to be positive. This also indicates that these are all endothermic processes, right? So look at this. This is 496 kilojoules per mole. Now, the third step. In third step, we take up chlorine gas, half a mole. And this chlorine gas, half a mole, is then converted into atomic chlorine. For this, the bond between two chlorine atoms needs to be broken, and this is called, therefore, the bond dissociation enthalpy. And this is about, for chlorine, it is about 121 kilojoules per mole. So look at this, the standard bond dissociation enthalpy, d by 2 is equal to 121 kilojoules per mole. The fourth step now would be the dissociated chlorine atom gaining one electron and getting converted into, getting converted into a chloride ion, and the energy involved here would be nothing but the electron gain enthalpy. So let us find out, the electron gain enthalpy of chlorine. Now, if you talk about the electron gain enthalpy, right, one electron is gained by chlorine, and this results into formation of chloride ion, and this chloride ion generally is the enthalpy involved here is about 349 kilojoules per mole. For the first time, you find that this energy value is negative, and so this process is an exothermic process. Remember, electron gain is most of the times an exothermic process, while rest of the processes were endothermic. This process here is an exothermic process, right? You can see the standard electron gain enthalpy, which is about 349 kilojoules minus per mole. So after chloride ion gets formed, right? What do we do here? After the chloride ion gets formed, we will have to think about the sodium ion and the chloride ion uh, forming the crystal now, ionic crystal, the NaCl. And for this, the energy which is involved here is called lattice enthalpy. This value is always exothermic, and it is always negative. Thus, the standard lattice enthalpy for NaCl crystal is about minus 787 kilojoules per mole, and this is this value is generally given experimentally and not calculated theoretically. Here, this value which I'm giving you is an experimentally evaluated value, and we would be for now using this value as such so that we can understand this theory. But otherwise, these values have to be calculated experimentally. Now, overall, the enthalpy of formation of NaCl, therefore, as per the Hess law, can be given as enthalpy of formation of NaCl, which is the sum of the enthalpy of sublimation plus enthalpy of ionization plus enthalpy of dissociation, and then you have the electron gain enthalpy, and then the lattice enthalpy, right? You know that most of these values can be evaluated experimentally. Even the enthalpy of formation can be evaluated experimentally. The only value which cannot be evaluated is this lattice enthalpy, the delta H0 H, the U part, which is not known theoretically. This enthalpy of formation, the overall enthalpy of formation, is obtained by adding up all of this, and this comes out to be minus 411 kilojoules per mole, right? Thus, this value, which is given enthalpy, the lattice enthalpy value, that can be evaluated experimentally. Now, so this is the entire thing. The overall Born-Haber cycle can be shown for the formation of NaCl crystal can be shown as under, and now you can see that there is this Born-Haber cycle which we can draw for NaCl, right? You can see that first of all, it is the overall reaction which I'm showing. Na solid plus chlorine gas half a mole, and this gives you NaCl solid, the lattice. Now we have Na solid undergoing sublimation to form sodium gas. The energy involved here is enthalpy of sublimation, and this gives you sodium gaseous form. This will lose an electron to form sodium ion, and this is the enthalpy of ionization. In the same way, now we will have to do for chlorine gas. Chlorine first of all undergoes dissociation from chlorine atom, right? The energy involved here is dissociation enthalpy d by 2, and the chlorine atom which is formed then would gain electron to form a chlorine ion or a chloride ion, and these the sodium plus and the Cl minus would come together and then give you NaCl crystal. While the crystal gets formed, a lot of energy gets released. This energy is nothing but the lattice enthalpy, and this is the overall Born-Haber cycle for NaCl.